elements having mass number in between 30 and 170, they almost have a constant value, that is for binding energy per nucleon. So once it becomes unstable, automatically it undergoes the decaying process, or simply it splits up into two or more nuclei. So sun is not actually burning, it is exploding with huge amount of energy every second. The atomic bomb is a principle that is relying completely on fission. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we are going to continue our story on nuclei. So let's see what nuclei holds for us. So again, in the last session, we were discussing about what is the binding energy to the mass number, that is, that particular relation was plotted to a graph. So what are the specialities and observations of that particular graph? That was being discussed. Now it's time that we write down that particular observations and what are the conclusions of these particular inferences. So what are the observations? The observations again are very much clear, that is, binding energy per nucleon is almost constant for elements that are in between 30 and 170. That is, elements having mass number in between 30 and 170, they almost have a constant value, that is for binding energy per nucleon. The second point is that the curve reaches the maximum point, that is, the graph has the maximum value, that is for iron, that is 8.75 mega electron volts is the binding energy per nucleon, that is for iron atoms. And then it falls down to 7.6 MeV, that is after going very high, then the graph gradually falls down, that is here the peak point is 8.5 MeV, then it gradually falls down and then it continues at 7.6 MeV, gradually falling down to uranium-235. So the highest peak value is attained by iron, which is having 8.75 mega electron volts. And then binding energy per nucleon is lower for both lighter nuclei and heavier nuclei. Again, I told you every atom wants to be more stable. So if it can remove one or two nucleons and be stable, then it will prefer that. So the lighter nuclei will also prefer that, and the heavier nuclei will also prefer that. So at both ends of the spectrum, that is, the lighter nuclei and the heavier nuclei both won't mind losing one or two nucleons, and hence for that particular reason, the binding energy per nucleon for lighter atoms and heavier atoms will be very low. Now, what are the conclusions of the graph we just interpreted right now? So the conclusions are also very simple. It states that nuclear force is a very strong and attractive force which is operating at a very short range. So nuclear forces are actually one of the strongest forces in the universe, and it is actually a very short range force, and we can say that that particular force is attractive in nature, producing a binding energy of a very few MeVs, or simply we can say that binding energy produced per nucleons inside the nucleus will be in the range of a few mega electron volts. And just like that, the constancy, that is the constancy of binding energy range, that is we saw that from 30 to 170, in between that atomic number, the value was almost constant. That is because, again, it is stating that this particular nuclear force, or simply the strong force, is actually very short in its order of influence. That is, we can say that it is a very short range force. So again, and the last thing is that two nucleons which is having lower binding energy per nucleon can combine together and release energy. Just like that, one heavy nuclei can actually split into two lighter nuclei, releasing energy, given that the binding energy per nucleon is very low. If it is highly stable, it won't do that. Again, it is just talking about the stability of the nuclei. So again, these two principles we have already know what they are, and we are going to study them in detail the very next topic, that is fission. So the first one is fission. So what exactly is nuclear fission? All of you might have seen the Oppenheimer movie, or maybe you have heard about the atomic bomb. The atomic bomb is a principle that is relying completely on fission. So what exactly is nuclear fission? Fission means it is splitting. So what is nuclear fission? It is splitting of a nucleus. So how exactly is that happening? Imagine that there is a big nucleus which is having a low binding energy per nucleon. So it is having a low binding energy per nucleon. Let's say for now it is uranium-235, or let's say it is cesium or zirconium, or just like that, any element which is having a lower binding energy per nucleon. So this particular uranium-235 is a heavy nuclei, and it is quite unstable. So like anything in this particular universe, it always likes to be more stable. So how can it do that? So this particular heavy nuclei, if given the option, is happy to split up into two or more. That is, it can be two or more number of lighter nuclei. That is, it can form into, or it can decay into krypton and barium or any other element. So it can either become two or more constituent elements if it is given a chance to decay. And that particular process of decaying, producing newer elements, will release huge amount of energy. That particular huge amount of energy is released as gamma rays and fast moving neutrons. This particular process of a heavy nuclei splitting up into lighter nuclei is known as nuclear fission. So again, how exactly does fission happen, or how can we make fission possible? So again, the way we make fission possible is that first get a fissionable material, that is a material which is loving to just split up. So that kind of material is known as a radioactive material or a heavy nuclei. That particular material in this particular case is actually uranium-235. So what we do with this particular uranium-235 is that we make it unstable. So the way we make it unstable is that we take one fast moving neutron and we just throw it at one uranium-235 atom. So imagine that there is one uranium-235 atom. We'll take one neutron and we'll just smash it into the center of the nucleus so that the nucleus will have one additional neutron, which means that now this uranium-235 is converted into uranium-236, which is completely unstable. So once it becomes unstable, automatically it undergoes the decaying process, or simply it splits up into two or more nuclei. So there is actually two variations that is possible. That is, either it can split up into barium and krypton, or simply we can just say that this is the most common thing that happens, but there is a possibility that this particular reaction is also possible. That is, it can either split up into barium and krypton, or it can split up into, this is antimony and niobium. So again, I'll tell you what exactly happens. You take a fissionable material, for example, uranium-235, you bombard it with a fast-moving neutron, automatically it becomes unstable. And in this particular case, the heavy nuclei actually breaks apart, splits into multiple other lighter nuclei. For example, in this case, it is barium and krypton. And there will be production of additional 3 more fast-moving neutrons. Now, what happens is that if I bombard one neutron with, if I bombard one neutron with one uranium atom, it will produce 3 other neutrons. Now, these 3 neutrons are ready to mingle with other 3 uranium atoms, which will again produce 3 more. Like this, 3 more, each of them will produce. Now, it is not producing new elements and neutrons only. It is producing huge amount of radiation, that is huge amount of energy in the form of radiation. Specifically, we can say that it is in the gamma ray region, or simply strong or high energetic gamma rays are being produced. So that is the effect of atomic bomb. When atomic bomb explodes, the fissionable material inside is actually uranium or plutonium. That particular radioactive material actually disintegrates, or we can say that it fissions, or it splits up into lighter nuclei, producing huge amount of energy. So when that happens, gamma rays are actually released. That is, fission happens. This particular process is known as fission. Heavier nuclei splits into lighter nuclei, that is fission. Plus neutron, that is a fast moving neutron is produced. In this particular case, 3 fast moving neutrons are produced, and with that high energetic gamma rays are being produced. That is, plus some MEV, that is some energy is also produced. That energy is in the form of gamma rays. So it is also produced. That particular gamma ray is very deadly for us. It can even penetrate concrete and even lead sometimes. So it is very deadly for us. That is why we say that the radiation is not good for us. So again, this particular reaction, if this is allowed to continue without any control, then this will just keep on spreading, right? Each one will produce even more, and this will just keep on happening. Now, if this keeps on happening, then we say that it is called an uncontrolled chain reaction. It is called an uncontrolled chain reaction. If it is an uncontrolled chain reaction, it means that it is a huge release of energy, or simply it is just a bomb. It is a bomb, which means that it is the principle behind an atomic bomb. An uncontrolled chain nuclear reaction is known as an atomic bomb. What if it is controlled? If it is completely controlled, if I'm saying that, okay, I don't want this to go beyond this particular limit. I only want the reaction to go this particular limit. I don't want it to go beyond this. Then we can say that that particular reaction is known as a controlled reaction. That is, if I can control the energy output, if I can control the energy output of this particular reaction, I'm saying that, okay, I have this much energy, now stop it. That is enough. If I can control that energy output, we say that, okay, this is a controlled reaction. In that particular case, we can say that, okay, this controlled reaction, that is, we are controlling the bomb, how much energy it is releasing. In that particular case, we say that this will become a nuclear reactor. This will become a nuclear reactor. That is what is happening inside a nuclear reactor. Now, how are we controlling this particular nuclear explosion? It is very simple. We are using what is known as controlled rods. For example, we are using carbon rods. So when we use carbon rods, these carbon graphite rods actually absorb the excess neutron. That is the 3, 4, 6 neutrons which is running around. The carbon rods will actually absorb. And it is not like 1 or 2 carbon rods, it will be hundreds of carbon rods all around this particular nuclear reactor. So that if anything goes wrong, the control rods are reinserted very quickly so that the excess neutrons are absorbed. It is known as a fail-safe. People also try to flood it with heavy water. Heavy water is, instead of H2O, they use D2O. Again, it is another isotope of hydrogen only, but again, they use heavy water in order to control the chain reaction also. Many methods are there. Point is that if you control this particular reaction, it will be a nuclear reactor where we can extract the energy. That is, this excess energy will be used in order to heat up water. This particular water that has been heated up will be now converted into steam. That steam will be directed to a propeller or a turbine which spins at huge rates, which will again be connected to a generator which generates electricity. That is how we get nuclear power, or simply nuclear electricity. So again, we have a nuclear plant in India which is quite operational. The only fear is that this fissionable material is actually nuclear waste. If not handled properly, it can cause radiation sickness. It can affect generations, because again, you might have studied in chemistry that the half-life period of every element is this radioactive elements is in the range of 80 years, 90 years, 120 years, like that. That is, this will the uranium will degrade into zirconium and then cesium, like that. It will keep on degrading, but each half-life period will be around 120 years, which means around for 800 years the radiation will still be in the air, which is very deadly for us. It is not like an atom bomb exploding, because again, if an atom bomb is exploding, it will be there for like 500 years or something, or 300 to 500 years or something. But if a nuclear power plant is exploding like that, if it is leaking out radiation, and if it is allowed by the wind to pick it up, by the water to carry it around, then it is spreading at a global scale. So it is going to be a huge disaster. So that also we have to be very wary about. So again, that is about nuclear fission. Now, what is nuclear fusion? Now, again, it is very simple again. Instead of one heavy nuclei splitting into smaller nuclei, it is smaller nuclei which are combining in order to form a heavy nuclei. For example, hydrogen and hydrogen will combine in order to form a helium atom, and during this combination, energy will be released. So this is known as fusion. This particular fusion is what is happening inside the sun. Inside the sun, huge amount of hydrogen atoms are colliding with each other, and under the immense radiative pressure of the sun, they are squeezed in together so that their nuclei literally fuse together, producing helium atom. And after some time, the hydrogen will be complete and there will be helium atoms. These heliums will be squeezed together in order to produce the very next element and the next element, like sodium, lithium, like that, beryllium, like it will go on like that. So again, is this particular fusion process which is happening inside the sun possible in our small earth? Well, actually, it is really possible. You just need a strong enough magnetic field and fusion materials. For example, tritium is the material we actually use. So, tritium is the material we actually use for fusion. If you have enough tritium and if you have a controlled environment, for example, if you have a toroid which is almost like a donut shape, which will be used as a magnetic containment field. If you have that particular field, and if you have tritium and you have immense pressure and temperature, then you can actually fuse together these atoms. But that is very difficult, and the energy thus produced is not enough to compensate for the energy which is put in to produce that particular fusion generator. So that is why fusion is not actually possible on Earth. But again, we are improving. Maybe in the near future, we will have fusion generators also. So again, fusion also is what is powering hydrogen bombs. For example, atomic bombs used uranium, and then there was the H bomb. H bomb is the hydrogen bomb, which is the most powerful bomb we ever invented. That particular bomb uses fusion. Fusion produces even more energy than fission. So that is why fusion is much more, and it has no waste elements or no nuclear radiation or anything like that. That is why it is more preferred, but it is very difficult to achieve with our current technology. That is one problem. So again, what is fusion? Fusion is the combination of lighter nuclei which is having lower binding energy per nucleon. They combine together in order to produce a more stable nuclei which is having a higher binding energy per nucleon. So how exactly is fusion reaction achieved? Again, I told you that in order to overcome the Coulomb's repulsive forces, that is when two nuclei come close to each other, the protons and protons will actually try to repel away from each other due to Coulomb's electrostatic forces of repulsion. But if they are squeezed in using external forces, for example, the radiative pressure forces inside the sun, they will actually overcome this particular repulsive forces and they will merge together. That particular merging will produce fusion, and this is achieved under immense pressure and high temperatures. So again, fusion reaction is achieved by raising the temperature of the system. So particles have enough kinetic energy in order to overcome the Coulomb's repulsive forces. So again, if you're doing it on Earth, you also have to contain this entire field. For that, we use magnetic fields in order to contain the charged nucleons. So again, this particular reaction is what is happening inside the sun. That is the fusion of hydrogen atoms. So initially, hydrogen atom, that is 1H1, is combining in order to form the hydrogen which we know, that is 1H2, and it is producing a positron. Positron is just a charged particle which is opposite in nature to that of an electron. It is the antiparticle of an electron, and it is also producing a gamma ray along with some energy. So this is the first step in the reaction. The second step is that this particular hydrogen atom is now being formed into what is known as deuterium. Deuterium will now be formed into tritium. That particular tritium will help facilitate the formation of helium atoms. In that particular process, it will release a huge amount of energy also. This energy is what we are actually interested in. As a byproduct, there will also be huge amount of gamma rays which are coming out of the fusion reaction. So again, we can see that here the positron and the electron will annihilate each other. When minus and plus comes together, they cancel each other out. In nature, it is quite a chaotic process, which means they will annihilate each other, producing more gamma rays and a huge amount of energy. Then again, as I told you, the deuterium and the tritium will combine together in order to produce almost the finished helium along with gamma ray and some form of energy. And finally, the helium, the almost ready helium, will combine together with one more hydrogen atom and it will produce the helium which we know and two pairs of hydrogen which will facilitate even more fusion reaction and a huge amount of energy from that fusion process. So sun is not actually burning, it is exploding with huge amount of energy every second. That is what is giving us our heat, our light and our energy. So know that sun is just a big bomb which is exploding every seconds with tons and tons of energy. Now that is nuclear fusion. So that is all about fission, fusion and binding energy per nucleon. I hope you have understood a little more about the tiny world of nucleus. I'll see you all very soon with some interesting electronic concepts. Until then, thank you.